Okay. Looks good to me. All right, so I'm going to continue with calculus today. Actually, I think it's going to be the last day I talk about calculus, and then we're going to go into some linear algebra next. But of course, I'm open to any other suggestions as well. I kind of want to make it as approachable for like a general audience as possible, at least at the beginning, and then I can go into more advanced stuff later. So we're still doing differential calculus, and this last section I'll be talking about implicit differentiation. Hopefully you can see the board good or well. So this will be lesson 10. Implicit differentiation. Hopefully you can see that. Maybe I'll switch to red. I think this is good. All right, so what is implicit differentiation? We're basically going to assume that we have a relationship between two variables and that one is a function of another, and try to deduce things about the derivative of that implicit function. So the most common example is like a circle. It's a relation that's not necessarily a function. Well, it's not a function at all. It doesn't pass the vertical line test, right? So you have a relation which describes the points on the circle. If it's radius 1, then this is the relation x squared plus y squared equals 1, right? Where we're thinking of these points in the xy plane. Right, so every point every point on this circle satisfies this equation at some point. Like here, there's some point square root of 2 over 2, negative square root of 2 over 2. And if you square the x and you add the square of the y, you do get 1. So this is a point that satisfies this relation, and every point on this circle is some point satisfying this relation. Turn up the brightness so I can see it a little bit better on my computer. Okay, and so there's a theorem that we're not going to go into in real analysis that basically says, if you have a relation like this and there's certain conditions, that locally, if you look at most of the points, it will be a function, one of the variables will be a function of the other. So in this case, like if I pick a point here and I look close enough, we can describe this, I'll put it in green now. We can just describe the points that are close to the point that we picked as some function of the x variable. So these can be described as some points x, comma, f of x. For some f of x, and maybe if we look at a different point, it's possible that this f here changes. Like basically all these points are the negative square root, and all of these points are the positive square root function. Right. So basically, we have some relationship between multiple variables. It'll probably just be 2 in this case because we're dealing with calculus in one variable. But we have some relation that describes some points, and then if you look close enough, there should be some function that describes one variable in terms of the other. And we want to know what is the derivative of that function. So we don't necessarily know what the function is. It's implicit. It's like implied by the relation, but we still want to know, since abstractly this function must exist, what would the derivative be at these various points? So this is a common thing in calculus. You have some relationship between your variables, but you don't necessarily want to solve for one in terms of the other and get a function. But you still want to know some sort of rate of change information, some sort of derivative information. Okay, so circle, pretty common relation. course, if anybody's watching and you want to ask a question at any point, let me know. We're just covering some basic, well, we're finishing up covering calculus now. Some basic differential calculus. Later, we'll probably go into integral calculus and multivariable stuff, but I'm going to hold that off for a few weeks. Also, if anybody's watching, happy holidays, Merry Christmas, if anybody celebrates. Okay, so let's look at an example from the Stewart textbook, the calculus textbook that we've been following. What's better, green or blue? I think green. Okay, so this is 3.5 in the calculus textbook, Stewart. Technically, I have the Stony Brook edition, if that matters. I think it might change some of the problems, maybe. But this is page 214, 3.5 section. And it says, find the derivative by implicit differentiation. So dy over dx. Okay, and it's very similar to the circle we were just looking at, but instead, oh, and by the way, this is problem number 3. And it says find the derivative by implicit differentiation, and we have the relation x cubed plus y cubed is equal to 1. So very similar to the circle, this is like all of the points on the circle described by a p norm, where the p is equal to 3 instead of 2. So it's like some sort of circle in some weird metric space, and it's all the points that satisfy this. So it's some sort of like elongated circle, and we want to know what's the derivative at any of the points that satisfy this relation. So any of the points that are on the curve. And so how do we solve this? So the kind of the easy way you want to think of it is you just want to take derivatives of both sides and then solve for the derivative of y. Right, and we're going to use what we learned last time, which was like the chain rule, product rule, stuff like that. That's going to show up because when we take a derivative of something that depends on another variable, like in this case y is going to be a function of x, we're going to assume that y is a function of x. Then when we take the derivative of anything involving y, we're going to have to use the chain rule, because like for instance y to the third power, if we take the derivative, we're going to use the power rule to get 3y squared, but then we're going to need to multiply by the derivative of y with respect to x according to the chain rule. So basically, we're going to take derivatives of both sides. We're going to use our derivative rules. So we have sum rule, power rule, chain rule, quotient rule. I'm probably forgetting some. But right, so we can split the left-hand side into a sum of two derivatives. So the first derivative of x cubed is just 3x squared. And remember, we're taking the derivative with respect to x, not y, because that's what dy dx means, how fast y is changing with respect to x. So on the left we get 3x squared, and then when we take the derivative of y cubed, it's going to be very similar. It's 3y squared, but then we need to multiply by the derivative of y according to the chain rule. So I'll just write that as y prime. That's the same thing as dy dx. And then the derivative of 1, or sorry, I wrote this. Oh, I did it wrong on mine. Did it wrong in the notes. Okay. Right, so the derivative of 1, of course, is not 1. It's a constant, so the derivative is 0. But I wrote 1 in my notes. Okay, so we get so this relation implies a relation with the derivative, since I can take the derivative of both sides. So this derivative must be equal to this derivative, or sorry, the derivative of this must be equal to this, so this must be equal to 0. And now we can just solve for y prime, and then we'll have the dy dx in terms of every point xy. So this means that basically 3y squared y prime is equal to negative 3x squared. And if we just move the 3y squared over, so divide by 3y squared, cancel the 3's. So in the end, we're just going to get y prime is equal to, why does this not make sense to me? No, this is good. Okay, x cubed plus y cubed equals 1, so we took the derivative of both sides, right? So then, and then we moved the 3x squared to the other side, divide by 3y squared, so we just get x squared over y squared, right? Okay, that looks right. Negative x squared over y squared. All right, and then this is y prime. This is just notation for dy dx. So what we've deduced, we took the derivative of both sides. We used the chain rule for y since y is a function of x. So it depends on x. Derivative of x cubed is just 3x squared. Derivative of y cubed is 3y squared y prime according to the chain rule. And then the derivative of 1 is just 0. And then we moved, this stuff to that side, divided by 3y squared. The 3's cancel, and we get negative x cubed y. Negative x squared y squared. Okay. So like I said, this is some sort of I don't want to try to draw it too accurately, but it's some sort of weird looking circle box type thing. And what it's saying here is that if I look at a point, I don't want to try to pick a point on here actually. Well, we can try to pick one like 0, 1, for instance. So 0, 1 is going to have derivative 0. That's just saying that the derivative at this point is completely horizontal. So that checks out. That makes sense with our formula, so that's good. It actually doesn't make sense with the way I did it in my notes because I made a mistake. So that's good. Okay, yeah, so basically the derivative at every point that satisfies this relation is negative x squared over y squared. So if I pick a point on here and I want to know what's the derivative of the implied function at this point, I can just look at this formula and plug in the x and y, and then I should get the derivative at that point. And it also makes sense here that when x is positive and y is positive, that this derivative is negative here, and in the picture I just drew here, that does actually match up with the picture, because the derivative it's going down, it's negative. Okay. You can read that from here, right? Yeah. All right, so that's basically the idea. You have a relation between two variables. You assume one variable is a function of the other, and then what we're doing here is we're gaining some information about the derivative of that implied function. And this is also useful for inverse functions. For instance, we'll talk about the inverse cosine function here, which is a common thing that shows up in pre-calc and first-year calculus students. Okay, so we're going to start talking about the derivative of some inverse functions. So we have inverse sine, inverse cosine. These are the functions that sort of, undo the other function, right? So if we have, let's just talk about inverse cosine. right? So we have our normal trigonometric functions. These are, right, the initial idea is that you have some right angle. Right angle here, you have some angle theta here. You have some x, y, z here. And then we say that the cosine of the angle is going to be the adjacent over the hypotenuse, right? So it's x over z in this picture. And you might want to know, how do we go backwards? So this, I have to feed cosine a particular angle in radians. Remember, if you're doing this on a calculator, remember to switch to radians. But if I have an angle theta in radians and I plug it into cosine, it's going to give me back this ratio between the sides of the angle. Sorry, the sides of the triangle, the right triangle. But you might want to go the other way, right? So let's say I already know what the cosine of the angle is, and I want to go backwards. I want to know which angle has that cosine. So in this case, let's say that I knew what the cosine was. Let's call it t. Right? Then I can't necessarily figure out what the angle is because cosine is a periodic function. It repeats infinitely many times, right? It's this like wave function that goes up and down and keeps repeating over and over. But as long as I ask for the angle within a particular range where it doesn't repeat, where it only hits every value exactly once, then I can find that angle. And so that restriction, I believe, is usually between, actually, I forget what the book says, but I believe it's, you can obviously restrict it on any 2 pi period, but I believe they do, oh, now I'm going to mess it up. Negative pi over 2 to pi over 2? Or no, actually, you can't do every 2 pi. I think it's only every pi. Yeah, yeah. So as long as theta is in this range, and a negative angle would be like something down here, right? As long as theta is in this range, then I can actually recover the angle uniquely. Given the cosine of the angle, I can apply the inverse cosine function to both sides. Equals inverse cosine of t. Right, so assuming on this domain for theta, this function is actually bijective, then there's an inverse function. We call it cosine inverse, or arc cosine is another name. So the arc cosine of the cosine of theta on this range always gives us back just theta. And that's kind of how these inverses work, right? So if I apply the inverse to the function that it's an inverse of, I just get back the variable that's in the input, so I just get back theta. So here we're just saying that the angle is the arc cosine of t, whatever that original the cosine was, this t value. Okay, so the inverse cosine is basically just saying, I like thinking of it as a question. So given the cosine of an angle, can I figure out what that angle was originally? And the answer is, as long as it's in this range, then yes, I can just apply this arc cosine function to whatever this number was. And then I should get the angle. But of course, remember, O is in radians. If you forget radians, the calculator is going to give you the wrong answer, or your teacher is going to give you the wrong answer. Either or, it's not good. Right, so in this range, we have this arc cosine function. And we want to know, so one of the, what's a common thing? Now we have a function. What can we do with it? We want to ask what's the derivative of the function, right? So arc cosine, how do we find the derivative? Well, we're going to use implicit differentiation, everything we've basically just been talking about. And it looks kind of tricky. It looks like you're maybe, applying some sort of trick, but it's all sort of straightforward if you just think about it long enough. So we're going to start with the inverse cosine of an angle, and we're going to try to find the derivative using implicit differentiation and sort of like some sort of logical argument for why it should work. And also, I want you to pay attention that this argument sort of works for other inverse functions. So you could use a similar argument for inverse sine, for the inverse of the exponential function, which is the logarithmic function, etc. Right? Okay, so here, let's say that y is the function arc cosine of x. So this is the function that we want to find the derivative of, right? Well, we don't know what the arc cosine's derivative is, right? But if we take the cosine of both sides, we can sort of cancel this arc cosine, and I can get an implicit function of y in terms of x, where it's not an explicit function, but we can certainly write that cosine of y is equal to x. What's that? So we have y is arc cosine of x. This is the inverse function of cosine. And what I did was I applied cosine to both sides, so we get cosine of y is equal to x, and this implicitly defines y as a function of x. Then I can take the derivative of both sides using our normal derivative rules and the chain rule. So cosine of y, the derivative of cosine is negative sine, so this is negative sine of y, and then because it's chain rule, I need to multiply by y prime, the derivative of the inside. And then on the right-hand side, we get the derivative of x is just 1. So I see somebody said, what's that? I'm not sure what you're asking, but if you can clarify the question, I could definitely help. So we have negative sine y prime. That's the derivative with respect to x. That's why we have to use chain rule. And then derivative of x is just 1. No chain rule needed. Right. Yeah, that's true. Yeah. X can only be in the range -1 to 1. Good point. And why is that the case? Because the output of cosine only takes values between -1 and 1, right? So it doesn't make sense to ask, what is the angle that has a cosine of 2? Because there is no angle that has a cosine of 2, right? So the chatter is saying that x can only be in this range, and they're exactly correct. Right? So again, we have an implicit function of y in terms of x. So we have cosine of y is equal to x. This is a relation between y and x. We can implicitly differentiate both sides with respect to x. We get this equation. And then now we can just solve for y prime. And then we have to sort of apply a little bit of trickiness, but I'll try to explain the best of my ability like why it works. So here we're just going to move this to the other side. So we're going to get y prime is equal to -1 over sine of y. And we could sort of stop here, but we do want to get y prime as a function of x. And that's only because we might want to take the derivative again, and it's kind of just easy to have it as an explicit function where we don't have to do anything, implicit anymore. So really what we're saying is, what is sine of y as a function of x? Because we know that y is a function of x, so sine of y is also a function of x. And so the question is, what is this function? So really this is sort of the answer, but it's not fully simplified. So we really want to see, what is this as a function of x? So we have negative 1 over sine y, and y is this arc cosine function. Okay, and right, yeah, but we want to explain why this is the case. Yeah, the chatter is giving the answer right here. So let me just write it again. So we have y prime is equal to negative 1 over sine, and then we had sine of y, but now we said y is a function of x. It's arc cosine of x. Right, so now we have written everything in terms of x, but we want to see why is the sine of the arc cosine of x equal to what the chatter is writing. And so there is a way to do it algebraically, but I like to draw out a picture. I think for students it's probably helpful to draw out a picture just to help you from maybe you're remembering something wrong. But I always like to go back to the picture of the triangle here. So we have arc cosine of x. So that's going to be some angle here, theta, where the, check my notes. Yeah, this is going to be an angle theta here where the length of this side is x, the length of this side is 1, and by the Pythagorean theorem that implies that this side has to be square root of 1 minus x squared, because this squared plus this squared has to equal to 1. And so we know that, so yeah, what we want to know is what is the sine of theta, right? Because theta is the arc cosine of x. It's the angle who has a cosine of x divided by 1, which is adjacent over hypotenuse. And so the sine of this angle is the length of this opposite side divided by 1. So it's just square root of 1 minus x squared, and that's what the chatter was writing in the chat. Okay, so basically it comes down to the Pythagorean theorem. Also, you know that sine squared theta plus cosine squared theta is equal to 1, so you can solve it that way. But this is just, a more visual way to do it. Yeah, and cosine of y equals to x, and then you use the sine squared plus cosine squared is always equal to 1, and then you can get it that way as well. Yeah. Yep, same thing. Yeah, the picture just really helps. I think when you draw the picture out, just makes it really, really easy. Then there's no, you're not really doing any algebra anymore. You're just kind of going through the, the trigonometry of it. Okay, so that tells you that sine of theta is this. So we know that sine of arc cosine is this. And now we can get our final answer, which is just basically that y prime is equal to 1 over square root of 1 minus x squared, where y is this arc cosine function. Okay, so that's the final answer. We have this inverse function, and we used implicit differentiation to find the derivative of the function, and we had to do some sort of trigonometry trick in the middle to kind of simplify it into... Now you can see it's much simpler, right? Because we don't have any trigonometric functions, right? It's just, we have, the function itself is a inverse trigonometric function, but the derivative doesn't have any trigonometric functions in it. It's just 1 divided by square root of 1 minus x squared. So relatively simple function, which is kind of interesting because you're starting with something trigonometric, and then the derivative turns out to be just this, rational, it's not rational polynomial, but it's pretty close. Okay, yeah, so we're going to go into something similar. Now it's going to be logarithmic functions. Now it's the inverse of the exponential instead. But like I said, you could do something similar for the inverse of the sine function, inverse of the tangent function. You just have to be careful, of course, where they're well-defined. And that's determined by, where are the functions one-to-one and onto. which domain in which range. Yeah, definitely. I definitely like the triangles. The triangle method is something I used to do in class, and I just thought it worked really well. It made my the chance of making a mistake much lower, I think. So now we're going to go into the derivative of logarithmic functions. Or not derivative. Well, I guess it is derivatives if you change the base. But derivative of logarithmic functions. I guess I will say derivatives. Right, so the logarithmic function is going to be the inverse of a particular exponential function that has a base. Usually we'll use base e, of course, the standard exponential, but you can change the base to be any number a. I believe it has to be positive or else I don't think it really makes sense. Like, yeah, because once you get to like -1 to the 1/2 power, now you're talking about imaginary numbers. So the base that you pick usually has to be positive. A is greater than 0. I guess it could technically also be 0, but that'll be boring. And then we're talking about the function a to the x. And you can prove that this function is increasing always. And a function that's always increasing is also 1 to 1. And you can show that it necessarily has an inverse also because of this 1 to 1 property or monotonicity. So we usually call the inverse the log base a of x. So this is the function where if I apply it to a to the x, then I just get x back, right? Log base a. So this is usually the notation. We just say log. We put a little base here, which happens to be a. Usually it's just e, or we'll just write ln. So log base a of a to the x is just x. They undo each other. And we're going to prove that the derivative of this log a function, so if y is equal to log base a of x, then we're going to show that the derivative of this inverse function, we're going to again use implicit differentiation, and we're going to show that the derivative is 1 over x log a. So 1 over x times log a on the bottom. Hopefully you can, oops. Drop my marker. So hopefully you can read this. But it just says again that if we have the inverse function of the exponential a to the x, so log base a of x, then the derivative function, or the derivative of that function is also a function of x, and it's 1 over x log a on the bottom. Okay, so let's show why this is true. That's a good time. But it's going to be a very similar exercise. But once you see this for the second time, hopefully you won't need to see it again ever again, and you can just be able to do any of these inverse functions. Okay, so let's prove the derivative formula. So let me just write again that we're using y is log base a of x, right? So that's implied that we have the relation that that a to the y, so these are inverse functions of each other, right? So if I apply the exponential a to the power of this, then I should just get x back. So if this is a to the power of y, the relation is telling me that a to the power of y is equal to x. Okay, and then we take derivative of both sides. The book actually tells you what the derivative of a to the y is, but if you didn't know, the way that you would figure out is you can rewrite this as e to the log a times y. And then you know that the derivative of e to the x is itself, so e to the log a y has derivative e to the log a y times log a y prime. By the chain rule, and e to the log a is just a to the y, so this is just a to the y log a y prime. And so that's what we have on the left here. That's the derivative of a to the y. So basically, I'm going to erase this in a second, but this is how you derive the derivative of a to the y. You use the chain rule, and you also use the fact that the derivative of a to the x is a to the x log a. Or you could just look in your book and see, oh, that's the derivative of a to the x, and you can just use that. But yeah, if you're not really sure, the way you derive it is you change everything into e to the x, and then you use the derivative of e to the x. But yeah. So maybe if you're a little confused about what I just said, you can look at the video later and pause it and go back. But we're going to skip that. We're just going to assume that we know what the derivative of a to the y is. I just derived it, but let's just assume that we just looked it up in the book. So derivative of a to the y, this is a to the y log a y prime. And the derivative of the right-hand side x is, again, just 1. With respect to x, we're taking the derivative. And again, now I can move everything that's not a y prime to the other side. So I get y prime is equal to 1 over a to the y log a. And we know that a to the y is just x. So this is really just 1 over x times log a on the bottom. Okay, and that's what we were trying to show, that the derivative was this thing right here. Okay, any questions? Zumbaka. Are you still there? Any questions? All right, and I'm just going to finish up with one problem, and other than just doing exercises and trying to get you guys to look at more examples of stuff, this also is an example of something I didn't cover the theory of, but I think when you see me do the problem, it'll kind of be sort of intuitive to you. You'll understand what the idea of what I'm saying is without me having to go into the theory too much. And that's this using implicit differentiation with logarithms. So I guess I don't want to go too in depth of it, but hopefully some of you know the logarithm properties. So like if you have the logarithm of a product, you can split it into a sum. So like log a times b is equal to log a plus log b. And you can exploit this in calculus. You can change, so instead of having to use product rule, if you have the product of functions, you can take the log of both sides, then you'll have a sum of functions, and then when you take the derivative, the derivative is linear with respect to sums. So yeah, I'm saying a lot of words here, so I don't want to confuse you too much, but let's go through this problem. Basically, the idea is that we're going to convert products into sums using logarithms, and then when we take the derivative, the problem is a lot easier. That's kind of the high overview of the idea. And of course, we're going to use the fact that we just figured out what the derivative of the logarithm is, so we can use the chain rule and stuff like that. Okay, so this is 226, page 226, 3.7 section. So page 226, 3.7, number 33, or problem 33. And so, again, pretty straightforward problem. They just give us a function, and they want to know what the derivative is. But of course, the functions are now getting increasingly more complicated. So this is 2x plus 1 to the 5th power times x to the 4th minus 3 to the 6th. Of course, this is just a polynomial, so we know that the derivative, we could just use the power rule on each term individually, and it's a sum of monomials, so we know that the power rule tells us the derivative for each monomial separately. But the problem here is that there's like, I think this is like a degree 5, 24, yeah, I think it's like degree 29 polynomial, which means it could have up to like 30 terms that we have to take the derivative with, right? But luckily here, if we take the log of both sides, then this is actually pretty simple in terms of logs, because this product of 11 things actually just becomes a sum of 11 things. So that's really the trick of this implicit differentiation with I think they call it logarithmic differentiation. So you're taking the logarithm of the function, you're taking the derivative of the logarithm of the function, and then you're trying to recover the derivative of the original function. And you're going to use logarithmic derivative rules, and you're going to use chain rule, and that's basically it. So take the log of both sides, and you're going to use the log properties, the fact that log turns products into sums. So if this is our function y is equal to this, that means that the natural logarithm of y is going to be 5 times the natural logarithm of 2x plus 1 plus 6 times the natural logarithm of x to the 4th minus 6. Right? Because basically we have this, like a product to the 5th power just means I have this times itself 5 times. Once I take the logarithm, it's like it's adding the logs 5 times. So I just have 5 log 2x plus 1. Same thing over here, we have plus and then 6 of these logs. Then if I take the derivative, so now the derivative of log of y is going to be 1 over y times the derivative of the inside function, which is y, so just y prime. And then now here's the tricky or fun part, where whatever your perspective is. But 5 times the log of a function, if I want to take the derivative of that, well, I can just use the chain rule. So it's 1 over this function times the derivative of the function. The inside function just has derivative 2 because it's 2x plus 1. So it's pretty straightforward. This is just 5 times 2 over 2x plus 1, which is 2 times the derivative of log of that, which is just 1 over 2x plus 1. And then it's going to be plus 6. And again, it's very similar, but now the derivative of the inside function is 3x cubed. And on the bottom, we have x to the 4th minus 6. Right. So to solve for y prime now, We have 1 over y times y prime is equal to all this stuff. So I'm just going to move the y to the other side. So we're going to get y prime is basically equal to y times all of this stuff. And again, sorry for erasing everything, but you'll see it all back up here again. So basically we have y prime is equal to y times 10 over 2x plus 1. There I did a little bit of simplification. We multiplied the 5 and the 2. And then plus 6 times 4 is 24. Yeah, 24x cubed over x to the 4th minus 3. Then we have a bracket around the whole thing. So y is times everything. And if we remember what y was this, product of all these polynomials, right? Where the first polynomial had 2x plus 1 to some power, and the second one had x to the 4th minus 3 to some power. So we're just going to have one less power of the 2x plus 1 for the first term, and we're just going to have one less power for the x to the 4th minus 3 for the second term. But other than that, everything will look the way it should. So the first term, we just get 10. 10 times 2x plus 1 to the, so we had to the 5th, but now we divided by one of them, so we have to the 4th, times x to the 4th minus 3 to the 6th, plus 24 times 2x plus 1 to the 5th, times x to the 4th minus 3 to the 1 less power, because it was to the 6th, now it's to the 5th, and then we're going to get that x to the 3rd term also, which just comes from up here. So this is the final answer. It's a sum of two terms. We have 10 times 2x plus 1 to the 4th power times x to the 4th minus 3 to the 6th power. This was 1 less power than the y term, because we had to divide by this term once. And then we get something similar over here. It's plus 24 times 2x plus 1 to the 5th power, which is the normal one, and then times x to the 4th minus 3 to the 5th, which is 1 less than 6th. And then we have this x to the 3rd term that we pull up here. So now everything is in terms of x. And if you really want some sort of sanity check, you can check that this polynomial is of degree 28, which is the correct degree since we took a degree 29 polynomial. We took the derivative, it should be 1 less degree, and if you look at the powers of this, I believe it's like to the 4th to the 5th, so this is 23, and then times degree 5, so 23 plus 5 is 28, so it is degree 28, and then this thing is smaller degree, but that doesn't matter. So we started out with the degree 29 polynomial. It was this product of all these further polynomials. It was one polynomial to the 5th power, and then another polynomial to the 6th power. We took the log of both sides, and then we used implicit differentiation, solved for y prime, and then kind of just simplified everything out here to get the final answer. The final answer was a polynomial of 1 less degree, so we know we did everything correct. Well, we don't know we did everything correctly for sure, but it hints, at least that we didn't make some error with the exponents or anything, most likely. But it doesn't guarantee it, right? You need to check everything. Okay, so that's all I have, I think, for today. That's implicit differentiation. And then probably on Friday, I'll start into some linear algebra stuff. I'm going to try to do like a little bit of theory. I don't want to do like completely all calculation stuff. So we'll get into, I really think the theory is pretty interesting for for linear algebra. And you can apply it to a lot of other areas, like into physics, into quantum mechanics uses a lot of linear algebra with inner products. So we'll probably get into inner products. I'm not sure if we'll talk about inner products or not, but yeah, I think that's it. So any questions? I'm not sure if the chatter is still in the room, but hopefully you guys follow. And if you need any tutoring help with calculus, of course, check out the email, mathpondofficial@gmail.com. Send me an email. We can talk tutoring. I can help. You can join the Discord server. Any of these things can help you out if you're a student or you're just really interested in math. Doesn't matter either way. Okay, I'll cut it off here.